first question starts off about the Poisson distribution, and we've got some information about the researcher. He believes a Poisson distribution with this mean of 1.75 is a good model for his orchids in a square meter, and he's looked at 150 areas. So this table shows his observed data. And then here he's calculated the expected frequencies, and he's calculated most of those. And he just wants us to find the value of R. So our model that he's using is Poisson 1.75, the same number of orchids in a square meter. So if X is number of orchids in a square meter, then what we're looking for, we want the probability X is greater than 5, which is the same as the probability X is greater than or equal to 6, which we can find from our calculator. Okay, and then we want the expected frequency, so that's the probability, and then our total frequency was 150, so R is that value, probability, times 150, which is 1.37. Look at the table, they're all to 2 decimal places, and the question even tells us to do it 2 decimal places. Right, so now he's going to do his test, so we want the hypotheses. So H0 is that Poisson distribution with lambda equals 1.75 is a suitable model. Okay, and so our alternative is that, remember, you could always shorten this, so Poisson 1.75 is not a suitable model. So your H0 always states what you're expecting. It's to do with how you calculate your expected frequencies. So we calculate our expected frequencies by assuming it's a good model. So H0 is that the Poisson distribution is a suitable model, because if it is, our expected will be the same as our observed. So that's H0. Right, so the test statistic was 2. It's important to keep that in mind, because that means they've already worked out the test statistic for us. Degrees of freedom is 4. We've got to explain why there's 4, which I've just typed here. So what we do is we look at our expected frequencies. R was 1.37. So what's happened is, this is less than 5, so we'll need to combine it with the closest category that makes sense, so more than 5 and 5, that makes sense to combine. If we combine those two, it's still not greater than 5, so we're going to have to combine it with the next category. So all those ones are going to become greater than or equal to 4. We're going to combine 3. So the last 3 cells are combined, and you have to explain why some of the expected frequencies are less than 5. Now that means I'm left with 5 categories, 1, 2, 3, 4, 5 categories. But then degrees of freedom was actually 4. Well, the degrees of freedom is 5 minus 1, because we always subtract 1, because the total frequency has to stay the same as we did to start with. So the total frequency here was 150, so it still has to be 150 with what I expected, so that's fixed. Right, now we're going to have to determine whether or not these data support the researcher's belief. Now they've worked out the test statistic for us, but what we need is to compare that to something. So this is a chi-squared. We've got our V is 4, and we've got our significance level is going to be 5%, it says in the question. So in your calculator, or using the tables in the back of the formula book, we can get that our chi-squared critical value is 9.488. That's with the 4 degrees of freedom and 5% level of significance. And I've just done that to 4 sig fig, or 3 decimal places. So what do we do? Well, our test is 2. That's less than our critical value. So we do not reject H0, or you could say it's not significant. What does that mean in context? So we're not going to reject H0. What was H0? H0 was that it was a suitable model. The researcher's belief, the way back we have a look, he believes that the Poisson distribution mean of 1.75 is a good model. So this supports researchers' belief. So you have to put it in context at the end of your hypothesis test. Right. So we've done the hypothesis test, and now he's working in another field, and this time number of orchids. So if the number of orchids in this field we're going to call Y, they come from a Poisson distribution with mean 1.5. Then he selects 200 areas and counts the number of orchids present in each square. And we've got to, very important, use a Poisson approximation. So the probability finds at least one square with exactly 6 orchids. So there's two things going on here. So first of all, we want a square to have exactly 6 orchids in. So this is going back to our looking at one square, and that comes from a Poisson distribution of 1.5. So the probability of having exactly 6 orchids in a square is probability y is 6, and using your calculator you can get that that's 0.00353. Okay, well what's he done? Now he's got 200 of these squares, so loads of them. Yeah, times 200 squares. So he's got an n of 200 squares, and he's got a probability of 0.00353 that each of those squares contains exactly 6 orchids. So if we say that O is number of squares with exactly 6 orchids, so now we're counting the squares that only the squares have 6 orchids in, then O comes from a binomial distribution with mean of 200, sorry, with n 200 and probability 3.53. Right, now we've done the first bit, the second bit of information. We get down to part E, the actual question. It wants us to use a Poisson approximation. So, if O comes from our binomial, then the mean is NP, which is 0.706. Okay, and we're going to use a Poisson approximation, so we're going to approximate using our mean, so lambda for Poisson is 0.706. So if I say that R for orchids comes from a Poisson distribution with 0.706, so this is where we're now using the Poisson approximation, and we want the probability that he finds at least one square with exactly 6 orchids in it. So actually what we're looking for is we want one or more squares with 6 orchids in it. So we want the probability of squares with 6 orchids being greater than or equal to 1. Now here's a really important point here, because it was a show that. Okay. Now yes, we could just do that in our calculator, but that's not going to show this probability, so we have to do some show. So what's that? Well, all probabilities have up to 1, and the only option we don't want is that the number of orchids is 0. So we're using OR might not be the most useful letter there. How do we work out number of orchids using is 0? Well, if you remember from your Poisson distribution or look up in the formula book, that's e to the minus lambda times lambda to the power of x. So if we do the probability over here of orchids equals 0, that would be e to the minus lambda times lambda plus to the power of x, x being 0, over x factorial. Now 0 factorial is 1, 0.706 to the power of 0 is 1, so we're just left with the e to the minus 0.706 bit. And then you can say that's 0.50638 and some more numbers, which is 0.50623 3 decimal places. And the important thing here is you're going to have to show this step, as this is a show that question, not just put it in your calculator.